Hello everybody, welcome to this talk about probabilistic data structures. So before starting, I'll tell a couple of words about me. I'm Andrea, I'm a software engineer. I do this job from around 25 years and I still love it. That's great, I think. And my main interest is in algorithms, data structures and AI. And as I was mentioning, today we're talking about probabilistic data structures, and we will apply those data structures to three different classes of problems: the membership, the cardinality, and the frequency. And as we'll see during this talk, these data structures will return approximate values. So unlike the usual data structures that we used to use, these ones may return false values, false information, but in what we gain for it is usually a lesser consumption of memory, which when you deal with a lot of data, it's quite important. So let's start with the membership class of problems. When do we use probabilistic data structures for membership? In general, when even if we get a wrong result from the data structure, it really doesn't hurt. So there's no correctness involved, but at most there's some more computation to do. And let's take the example of a taken username. So let's say that we want to check if a username is already taken on a specific domain. If the data structure tells us that it's not taken, while actually it is, well, whenever you try to insert the new value into the database, you will probably get an error because of the duplication of an existing value. So you just check this error, and then return to the user that the result that the username is not available. So it didn't really break the application, but actually it just made some more work. But for all the other times in which the data structure told us that the username wasn't taken and it actually wasn't, then we saved a lot of memory for getting that information. And this is just one of the examples where you can use them. For example, the Cassandra NoSQL database avoids checking the SST tables, the SS tables data files while merging data on disk using the Bloom filter. One of the data structures that we are going to see. Or for example, with the ad placement, as a user already seen a specific ad, so this is another information that relates to membership, as well as fraud detection. So the same user has paid from another location, from this location. So these are information that are used for fraud detection and can be efficiently managed by probabilistic data structures. So in this case, we're going to talk about the membership. So just checking if an item belongs to a set, nothing more than that. And we're going to see three different data structures, which are the Bloom filter, the counting Bloom filter, and the cuckoo filter. And we're now going to see them in detail. So let's start with the Bloom filter. It basically consists of a bit array of size m and k different hash functions. So whenever we want to insert an element in this Bloom filter, we just apply this k different hash function to the item. We get a number as an outcome of the hash function. We mod that value to the size m of the bit array, so to find an index for the array. And then we set that bit to 1. And how do we check if an item belongs to the set? Actually, we just check if all the bits that the hash function maps to are set. Okay, this is just a lot of talk. Let's see it. Let's see how it works with some diagrams, which is easier. So let's start from the top. Let's say that we wanna insert the X item. Then you see that there are 3 arrows coming out from the x, and the first one is the first hash function, which applied to x gives as a result 1, meaning these the index 1 of the bit array, meaning the second position of the array. So I set 1 to the bit to the second bit of the array, and then I apply the second hash function, which gives as a result 3. So this means that the fourth element of the array has to be set to 1, and the same goes for the third hash function. So I just set the 3 bits to 1, and then I insert y, the second row in this screen. It's the y. It's in green. We see also the arrows, and we set the first hash function. This is interesting. Collides with the value given from the first item x. So since the bit is already set, we just leave it set. So it was 1, it remains 1. And then the second and the third hash functions transforms the bit from 0 to 1. And then we insert another item, z in this case, which is shown in red in the third row of this diagram. And again, there's a collision. This time is the third hash function, which collides with the third hash function of the second element of y. And again, the bit was 1, it remains 1. So now, what can happen? If we want to check if an item belongs to a set, in this case, we want to check E. So we can see E below the array, and it has the 3 arrows mapping to the hash function. So the first hash function applied to E maps to the second element of the array, which is a 1. And then the second hash function maps to another element in the array, which is set to 1. But the third hash function maps to an element which is still 0. This means that E doesn't belong to the set. So if the Bloom filter is asked if E is belonging or not, it will return a false. It will return no, it doesn't belong. And that's a true negative, because if you see, we only have inserted x, y, and z. So E is not present. So it's correct. It's not there. And then we see another case. We want to check y. As we saw before, we already inserted y. So we the hash functions that map to applied to y map to 3 indexes in the array that are already set to 1. And so since all the indexes are set to 1, then it means that the item belongs to a set. So the Bloom filter will return a true. Yes, y belongs to the set. And actually it's true. It's a true positive, because we know that we inserted y before. And then it comes the weird situation. We want to check G. G wasn't inserted in the set, because as we see, it's just x, y, and z. But the hash functions map, the first hash function map to an element which is set to 1, the second does it as well, and the third does it as well. This means that G for the Bloom filter has been inserted, while actually it's not. So it will return a true as the request for belonging to the set, but actually it's not belonging, because we didn't insert it before. So in this case, the Bloom filter will return a false positive. As I said before, of course, we have to be aware that this can happen. So the logic of our application must be aware of the fact that it can return, the Bloom filter can return false positive and just behave accordingly. But where's the benefit in it? So if we want to compute, if we want to make sure that we have some kind of performance from our Bloom filter, and for example, we know that we are expecting a certain amount of items, of different items, and we want a specific false positive rate. And in this case, n is the number of expected items, and epsilon is the number of is the value of the false positive rate. Then m, which is the size of the bit array, must be given by this formula, and k, the number of the hash functions, is given by this other formula. So just to make an example in numbers, if we want to have a Bloom filter where we expect to have 1 million different items, with 1% error rate, so that every 100 of request of belonging, we get only one false positive. All the other 99 are true positive or true negative. So if we want to have that, then M must be, the size of the bit array must be 9.5 million, so it's around 1.2 megabyte in memory, and the number of hash function is 7. Now, the good point is that this is a capped size, so we know that whatever the size of the object we have in memory is, we don't exceed that amount of memory. So this is unlike, for example, using a set. So if we're just using a set and checking if an item belongs to a set, this of course it's linearly related to the dimensions, to the size of the object that you are allocating. In this case, since we are using as function to transform that into numbers and then into bits, then of course we have a capped size. So if we start from the right side of, on the right side of the graph, we see that if we want an 80% of error rate, which is really high, we have to have around 500,000 bit as the size of the array, which is divided by 8 in kilobytes, so it's around 60 kilobytes, so very few memory. And the more we want the error rate to decrease, the more the memory we need to do that. So the example that we saw is the one on the left, so we have 0.01, which is 1% of error rate, and then the number of elements is 9.9 million. So a nice thing about the Bloom filter is that actually I found that a scientific article in which some researchers found that the fruit flies olfactory neural circuit evolved in nature a variant of the Bloom filter to assess the novelty of odors. So it's not exactly Bloom filter because it adds 2 additional features compared to the Bloom filter that we just saw. So it's also based on the similarity to previously experienced odors. And then it also comes a time dimension on it. But the basic idea is the same. So a neural circuit that it's doing exactly what the Bloom filter is doing. But so here, just to see how it's easy to do that. So this is a 20 lines of code in Kotlin that implements it. It's not production ready, of course, but it works basically. There's from line 15 on, there's an hasher class which provides the hash function, and then the rest, as you can see, it starts from line 3, defining M and K, and then it defines at line 6 the hashers, and then you have only 2 functions. You have the contains function and the add function, which does what I described before. The contains just checks that all the hash function returns are set to 1, and the add just set the bit to true for all the hash function. Now we see 2 methods: contains, add. Usually there's also delete, but how could work a delete with the Bloom filter? So let's say that the current state is the last that we saw with these 3 elements inserted, x, y, and z, and let's say that we want to remove x. So if we want to remove x, we transform the ones into zeros, and what happens is that we remove the 3 indexes that we compute with the hash functions. But because of the collisions, when we delete the second one, we also delete the one that was used by y. And that's the issue, because if now, after removing x, we check y, it's a false negative, because it says that y doesn't belong to a set. So in this case, we would have true positive, true negative, and also false positive and false negatives. And this, of course, means that the data structure has no use at all. So Bloom filter simply does not accept deletion of data. Exactly. So a way to address this is to use a counting Bloom filter. which consists, instead of a bit array, it consists of a count array. So it uses not more a bit, but uses it uses a byte or an int or whatever other data type you want. And it also uses the k different hash functions that we saw before. The membership condition now is that all the counts must be greater than 0. So in this case, we insert x, we increase the value from 0 to 1 for x, then we insert y. The first hash function of y maps to the value that was already set to 1 by the first element, by x, and so we increase it to 2. And same goes with z, and we go on, and we increase the numbers. So in this way, we can just, again, check if there's a true, if we check E, we can check that all the values it maps to via the hash functions are greater than, one of those is not greater than 0, and so E is not belonging, because there's one element which is 0. And if we check Y, it's a true positive, because all the elements it checks to 2, 1, and 2, they're all greater than 0, so this means that it's belonging to a set. And then we have again the false positive case. G maps to 2, 1, and 2, but they were set by X, Y, and Z, not by G. So even though the Bloom filter thinks that G belongs to the filter, actually it's a false positive, because we didn't insert it before. But then there's the extra case. From this current state, if we want to delete Y, then we just decrease the numbers of the values of the indexes that the hash function applied to Y maps to. And in this case, it still works. There's, of course, a trade-off with this, and we will see it later. Here you can see that the main structure of the class is the same. There's just a new method at line 11, which is delete. And in this case, so the add is not anymore setting a bit to true, but it's an increase of a value, and the delete will decrease that value. The contain is not just checking if the bit is set, but if it's greater than min value. Yes, of course, here it's Kotlin, it's JVM, so the byte is signed. So to leverage the whole 8-bit of the byte data type, I just made it start from the min value for arriving to the max value. So the bad thing about the counting Bloom filter is that it uses a lot more memory compared to the Bloom filter. If we're using a byte, because we know that we won't have more than 256 possible increase of the values. The size of the Bloom filter will be 8 times bigger, and 16 times bigger with short data type, and 32 times bigger with the int data type. And the issue is that it might overflow. So it's probably not a good idea to use in a very generic case, but we have to know very precisely what the use cases of our application is. So another way to address these issues is to use the cookie filter. So the cookie filter is mainly based on the cuckoo hashing. So before starting talking about the cuckoo filter, just see how the cuckoo hashing works. So each item that we wanna insert in this filter, in the hash table, has two possible locations that are given by two different hash functions. Again, we're talking about using hash function to find a numeric value, to find an index in an array where to put some values. So cookie hashing has two hashing functions to have for two possible locations. And then we have, and then since we are inserting, we compute the hash function, we get the values, and if one or both these locations are empty, we just insert the item there, and okay. Otherwise, we select randomly one of the two locations, we kick out the existing item, we put the one that we want to insert, and then we relocate the existing item that was kicked out, we relocate it to the alternate location. And if the alternate location had already another item, then it's kicked out and it will go to its alternate location in turn, and it will go recursively until it finds an empty spot. So as you can see, of course, this has the issue that it might end up in a deadlock. And in order to resolve it, you have basically just to increase the size of the arrays. So let's see a practical example. Let's say that we want to insert x. Here you see the two arrows going up and down are the result of the two hash functions. So the first hash function applied to x gives 2 as a result. So it's the third element of the array b1, while the second hash function gives gives 9 as a 8 as a result. And then these are the two places where I can put the x value. Let's say that we put it in the b1, but we keep track of the other possible location where we can put x. So we keep an arrow from x to the other possible location. Then we insert y. So we apply the hash functions to y, and we see that they come out with the two locations. Both of them are empty, so we just insert y, and that's easy. And we keep track of the location of the alternate one. Then we want to insert z. Z, it's more interesting because z, the first hash function mapped to an element which is already occupied by another item. So in this case, we turn to the alternate location and we save z in the alternate location, and we keep track that it points to another location, which in this case it's already busy. Then we want to insert w. Now this is the issue, because the two hash functions map to elements in the array which are already occupied by two other items. So as I said before, we just randomly decide that w is going into the array b2, the second one, the bottom one. And then we write w in that position, and we kick out z. And then we check z as an alternate location. Let's go there. In this case, the alternate location is already occupied, so we need to do the same thing as we did for w. So we kick out x, and we write z in place, and x is moved to its alternate location. In this case, the alternate location of x is empty, so we can write it there. So this is how it works. And we will see later in the code how to address with the recursion issue. But what is cool about the cuckoo hashing is that the lookup runtime complexities is constant, because we only check, given the two hash functions, we have two places to check in the arrays. So it's really, really fast. The drawback of this is that the insertion can fail. As I said before, if there's a cycle, a loop in the kicking out system, then we have to stop doing it and resize the array to a more proper dimension. Incredibly enough, still, given all this stuff, the amortized runtime complexity for insertion is still constant. So let's get back to the cuckoo filter, because the cuckoo filter is based on these cuckoo hash tables. So the basic idea is that we use the hash table to put items, and then we use the check that we saw before, so checking in one location or the other to see if the item belongs to a set. And that is the membership condition that we are checking. So to save memory, again, the fact here, so until now we are using a normal data structure, because the cuckoo hashing is let's say a traditional data structure. It gives exact results. Where do we get the probabilistic data part? So instead of saving the whole object into the array, we save just a fingerprint, which has f bit of length. But then, if you remember when we kicked out items and we wanted to put in the alternate location, so if we don't store the item where to which we can apply the hash function to find the other location, but we just have f bits of its fingerprint, how can we track back the alternate location in order to do the insert that we saw before? So in this case, what we do is creating the fingerprint function, and that's fine. But then we have the two hash functions which are defined in this specific way, which is quite clever. And it is the first hash function is just a normal hash function, while the second hash function is the XOR operator applied to the first hash function and to the hash function applied to the fingerprint of the item. Given the symmetry property of the XOR operator, this means that we can get having the hash of the first item, we can get the fingerprint of the fingerprint of the second, we can get the second location, and vice versa. So this is the way how we get the alternate location even if we don't have the complete data in there. And here is where the probabilistic part comes out, because from a whole object we just get its fingerprint, and then of course this may have collisions, which is the basic of the false positive stuff. How for what it concerns the memory occupation, we have this ugly formula that shows us how many bits per key we use, but in general it's sufficient to know that this is slightly slower than the Bloom filter occupation of memory. So it's a bit better, especially for big hash tables, and it supports deletion. So if you need deletion, this is definitely, even if it's more complex, it's definitely something that you should check out for. Here you can see the code for the insert. I didn't put all the other thing because it's more complex, as I said before. It's interesting to note that at line 16 there's a for loop which lasts at most max kicks, which is a constant which we define according to the size of the items we want to insert, and we try to kick out buckets until this maximum number of kick out. If we reach that value, then we just return false, because we don't want we need to rescale the whole array for making room for all the items. And that's it for the membership part. So now we can start with the second class of problems, which is the frequency. And of course XKCD comes in help when there's something fun to talk about. And so what is frequency? Frequency, basically, it's just counting the number of times an item appears in a stream. And for doing that, we are using the count min sketch data structure. So when do we need this? So maybe we need to count the unique users of a service, or maybe the top K items in particular environments, or also in network traffic analysis. So there's a lot of use cases in which we need to know the frequency of the items. And so we are going to see the count min sketch data structures, which is composed by D hash functions. And then we need a bidimensional array, which I call count, which is of size D by W, where D and W are defined by some formulas, where defined based on epsilon, which is an error rate, and delta, which is its probability. So given these, again, as I did for the Bloom filter, if we know that we want an error to be at most of 0.1%, and with a specific certainty, in this case 99.9%, then I will compute this W and D with the formulas, the values of W and D, and then I know this matrix with this bidimensional array, which size as to have for doing it. So let's see how it works in practice. So this is the initial state. We have a bidimensional array. As I said, we have D. In this case, we have D, which is 4, and W, which is 16. So we have D hash functions, which are the rows of our array, and we have the number of possible elements for each function is given by W, so it's 16. So let's say that we want to insert X because we have a stream of items passing by, and then the first one is X. Okay, let's compute the first hash function. Let's apply it to 2, and we get as a result, in this case, 2. So it's the third element of the array. It is zero based, of course, and then we increase the value of the element of 1. So from 0 it becomes 1. Then I compute the second hash function, I apply it to X, and the result is 13, and then I write on that index on the array, I get the current value, which is 0, and I increase it to 1. And the same goes for the third and the fourth hash functions. Then I want to insert Y. So I apply the first hash function, it's 6, and I put a second number there. The second hash function gives me the same result as I get before, as it was as for X. So it's again 13. So in this case, I increase the existing value. So from 1, it becomes 2. And then I apply also the other ones. There are no collisions, so I just increase from 0 to 1. I insert again X. So now X is inserted again because it was the first item I inserted, and so I increase the values. Now are 2, 3, 2, and 2 because those are the values of X. How do I check how many times I've seen passing this item? So I get the minimum of these 4 possible values. For example, on the left you see count X, so I'm trying to see how many times I've seen passing X on my string. And I get the value of the count matrix. For the first row, I get the index of X applied by the first hash function. So basically, I'm just looking at the position in which the first hash function has mapped X, and then I just read the value there. And then I do it again for the second hash function, the third, and the fourth. And so I see that I need to compute the minimum between 2, 3, 2, and 2. This means that the minimum is 2, and actually it's a correct value. And if I want to count Y, then in this case, if I look at the positions, at the numbers in my matrix, I see that actually I need to compute the minimum between 1, 3, 1, and 1, which is 1. And again, it's true. So in this case, I got exact values, but this is a probabilistic data structures. This means that if there are collisions on the hash functions, I will increase numbers that will be used by also other items. And this means that I might have higher counts. So this is where the probabilistic part comes into. Of course, the good part is that I have a limited amount of memory, whatever the number of elements I get in my stream. And here is some code. There's nothing particular here, so I would just skip it. So if you have the at the end of the slide, there's a link to the GitHub repository that contains this code if you want to check it or just play with it. And then we can skip to the last class of problems that we want to solve with probabilistic data structures, which is cardinality. And we mean just counting the number of distinct items in a collection. And for doing that, we're going to use hyperlog-log data structure, which is actually an improvement over superlog-log data structure, which in turn is an improvement over log-log data structures. We will just see the last one because the main intuition behind all of them is the same. What they improved is the heuristic for getting the right numbers and correction values to get more precise numbers. So, when do we need the cardinality, this cardinality? Some commercial software like BigQuery, Snowflake, they can give you, if you are querying a database, a table, and you want to know the number of rows, you can either use the count, but you can also use the approx count in BigQuery, for example. This doesn't give you the exact number of rows, but it gives an approximation using hyperlog-log. And when you have a lot of data, this is a substantial saving in cost for doing this. And then there are also other use cases, but time is running, so I just get into the hyperlog-log. So here I want you to understand the main intuition behind the idea of hyperlog-log. So let's say that we have an amount of numbers, of completely random numbers, and think about their binary representation. So with this big set of numbers, you can safely, if this is random and big enough, you can safely assume that half of these numbers, their binary representation will start with 0, and the other half will start with 1. I think it's quite safe to assume that. But again, we can go a bit further, and we can say that 1/4 of all these random numbers start with 0, 0, and another 1/4 starts with 0, 1, another 1/4 starts with 1, 0, and so on. And I also put the 1/8, which I won't read because my tongue is starting going on its way. But the main intuition is this one, of course. So the general rule is that the probability of having the first k bit of a random number be inside a big set of random numbers is 2 to the minus k, so 1 over 2 to the k. This is the main intuition. And how does hyperlog-log work? So let's imagine that we have a very big set of items that we use hash functions to transform into numbers. So when we insert a new item, we get the number associated by the hash, and if it's starting with, for example, 4 zeros, then we can say that it's likely that the set has a size of 2 to the 4th. So 4, 0, 2 to the 4th, as we saw before. So this has very big caveats, and the first one is, of course, this works with big cardinalities, because of course if we have a set of 5 numbers, this won't work at all. But of course we saw that we are using it to save memory, and this comes when you have a lot of data. So of course we will have big cardinalities. And also the hash function must return uniformly distributed binary representation, because if we have skew in the hash function, of course that will be represented in the values as well. So how does it work? It consists of a hash function, the one that we saw before, and an array of integers, or long, so it depends, but still an array of some numbers that we call m. So what's the main problem here? Since we have only one hash function, we risk that a particular number with a lot of leading zeros might be just an outlier, because all the others do not have so many zeros. And so instead of using just one hash function, we could use multiple ones. But that's, of course, it's a waste of time. So it uses a clever way to use just one hash function, but distribute it as if they were multiple ones. So let's say that the hash function returns a 16-bit number. We just take the first 4 bits and we pretend that these 4 bits represent a number, which is in this case 4 bits, so 16 possible values, and this is let's say like 16 different hash functions. And then the rest of the representation is just the hash value itself. So in this case, let's see how it works practically. We want to insert x. X is mapped by the hash function to this number, so we know that the index in the array M is given by these first 4 bits, which maps to the decimal value of 12, and so I will put a 1 on the 13th position, sorry, on the 12th position in the array. And what is the number of leading 0 in the remaining part of the hash value? It's 1, because we have 0, 1, 1, 1, 0, 0, and so on. So there's just one leading 0. And so we put a 1 in there. Let's say that we insert y. Y, the first 4 bits map to the index 5. So I will put that value into the 5th index of the array. And we have 4 leading zeros. And so I will write 4 in there. And then I hash z. Z maps to the same index as one item that we inserted before, but it has only one leading 0, and the value was 4 before. So we don't change it because it's lesser, and we keep it the one that was existing. So in this way, we fill up the array with all these values, and how do we get the cardinality? So we compute the normalized harmonic mean of the values of the M array, and then the cardinality itself is given by this harmonic mean applied to a correction factor and to the square root of the cardinality of the array itself. So these numbers are were found with the heuristic process for finding the better representation of given this different size of the M array. Those were the best values that mapped to the actual cardinality. So let's make an example. Let's say that the array M contains these numbers, which are the result of inserting all the items that we saw before. So the cardinality is given by these numbers, which are given by the formula that we saw in the slide before, and the result is 124. So this is the estimated cardinality of the set. But then let's see the second example. You see there's one highlighted item, which is the third one. It's not 2 anymore, it's 12. So it's 12, it's a lot more. So here we are assuming that we have 12 zeros in front of the number. So they're all zeros. And 2 to the 12, it's 4,000. But the cardinality given is 152. This is because the harmonic mean lowers down the outliers, so that we avoid that one single value that would skew everything actually corrupts the estimation of the cardinality. And also the fact that we have divided the outcome of the F function into different values mimicking different hash function also allow us to avoid outliers and skewing. So from this point of view, the hyperlog data structure is really efficient. And with this one, here is just a simple implementation. Again, you can see it on the GitHub code. And here you can find some links. Actually, these are the links of the original papers that describe the data structures that we saw before. And also this is, there's also the link for the GitHub repository that contains the code that you saw. And with this, I thank you for having listened to this talk. And if there are questions, I'm here to answer. Thank you. So no questions, it means two things. Either I was extremely good in explaining and no doubts, or I messed it up so much that nobody has the courage to say, hey, I didn't understand nothing, could you repeat everything? I guess it's not that, it takes some time to digest. Yes, I also get. Oh.
I thank you for a presentation, very interesting. Do you have any practical implementation or usage of those filter?
So you mean, yeah, there's so the practical implementation you can find libraries that.
No, practical in the sense that you'd use that for a project, for example, counting user on a portal, or for example, streaming or something like that. So are you using that in a real world?
Yeah, I used it in the past some time ago, but I used the library to do that. Okay. Yeah, it was sorry, it was the Bloom filter basically. But
for which project? If you can't
it was a project related to. It was quite complex. It was to a refinery, an oil refinery, and there was some specific items that we had to check that belonged. So from a very big set of there were the combination of possible fuels that can have that was a really huge number. We need to check if that one was already seen before or not. And instead of putting all of those in memory, because the objects were quite big, actually the Bloom filter was quite efficient, because with a very limited amount of memory, we didn't need a really high efficiency, so that the error rate could be also low, high compared to other things, because there was not much computation involved in recomputing the stuff, but since we had to run with severe memory limitations, we needed this data structure to be very limited. And especially, we did want to have a capped side, so that we didn't have allocation other memory in the moment in which we saw other items we didn't see before. So that was the practical use.
Thank you very much. Thank you.
Thank you.
Anybody else? Yeah?